Good morning, cherubs. So today's lesson is on isotopes and nuclear radiation. All right, so before we begin on that, we're just going to do a little bit of a recap on P, N, and E. So remember that this is the nucleus of an atom, then you've got the electron shells, and then you've got electrons in that shell. Within the nucleus, you've got positive charges and neutral charges. So you've got your protons and your neutrons, and your electrons are obviously negatively charged. Now, remember that from the two numbers that you are given in the periodic table, where you have your mass number and your proton or atomic number, okay, remembering that this number here, okay, is our proton number, so that is obviously 6. Then our protons, because our protons and our electrons, our positives and negative charges have to balance out, our electrons would also be 6. And then the difference between these two numbers, because remembering that this is protons plus neutrons, this is protons only, and then technically also electrons. Okay, that 12 minus 6 is 6. Okay, now then, this isn't the full story, okay, because some atoms have radioactive isotopes, okay, and carbon is one of them, okay. So this is carbon-12, so this is the normal element that you find in the periodic table and you find most of the time. However, carbon has an isotope, okay, and it's called carbon-14. So obviously you can see you've got a difference here. Okay, now then, this number is the same, so it must mean that our protons remain the same. So that must mean that our electrons remain the same. So the difference here must be in the neutrons, okay? So what you've got here is you've got 6 for 14 minus 6, which gives us 8. So as you can see, the difference here is that carbon-14 possesses 2 extra neutrons. And this is actually what the definition of an isotope is. So the definition of an isotope is an element that has the same number of protons and electrons as the normal, quote-unquote, element, but a different number of neutrons. Now then, because it's got a different number of neutrons, that makes this nucleus unstable, because there's extra things in there that shouldn't be in there, all right? Now, isotopes are unstable, so they decay into more stable elements and give off radiation in the process known as radioactive decay. All right, so just quickly here. So radioactive isotopes can spit out one or more types of ionizing radiation, and this is all down to the fact that it has extra neutrons in the nucleus that shouldn't be there, and it makes it all unstable. Now, there are 3 types of radiation, okay? Alpha, beta, and gamma. Okay, now if you are into the Marvel universe, okay, you've probably come across gamma radiation before. As far as the Hulk is concerned. However, sadly, that is not one of the uses of gamma radiation. I do apologise. However, we'll start with alpha. Okay, so alpha, and this is the symbol for alpha radiation. Okay, it's made from, it's made from 2 neutrons and 2 protons. It's sometimes referred to as a helium nucleus because a helium nucleus has 2 neutrons and 2 protons in it, okay? Now, this means that overall, an alpha particle has a positive charge, okay? Now, as you can see, in the grand scheme of things, okay, being made up of 2 subatomic particles makes you quite large, quote unquote. So it's large, which means that it's slow moving, and it's strongly ionizing, okay? Now, this is a term that pops up quite a lot. Ionizing is just the ability the radiation has to knock electrons off other atoms and turn them into ions, okay? And ions are charged atoms, okay? We'll get more into that later on. So if you are strongly ionizing, it means that you can do that quite quickly. And that's obvious because it's quite large and it's got a positive charge. It means that the alpha radiation is quite good at ionizing. It's quite good at bumping into things and knocking electrons off. All right, bumping into atoms, should I say, and knocking electrons off. And that's all that strongly ionizing means. Okay, now then, because alpha is so large and slow moving, it's actually stopped by a thin sheet of paper, or indeed your skin, which is why in medicine you would never usually get an alpha source as a tracer. Okay, because it's stopped by paper. It's actually alpha is also one of the more dangerous types of radiation if it's internal. So if you like eat it or drink it. Okay, that shadows my cat, Izzy, by the way, just FYI. Now then, alpha, because again it's so large and slow moving, only travels a few centimeters in the air. Okay, now the next type is beta. And beta is fast moving and is an electron. Okay, so it's got a negative charge, this one. So alpha's positive and beta is negative. Now, it has no mass because, as we've talked about, okay, the mass of an electron is 1/6,000. It's negligible and it is moderately ionizing. Okay, so it's not strongly ionizing, it's not weakly ionizing. It's that wishy-washy term of moderately ionizing. Okay, now that I've put in brackets there that this happens is because a neutron changes into a proton in the nucleus. I will get more into that in the upcoming lessons, okay, but not right at this moment in time. All right, do apologise. Now, beta, okay, which is the symbol here, beta is stopped by a 5mm sheet of aluminium, okay, and it travels a few meters in the air. All right, now then, last one, which is probably the one you're more familiar with, is gamma radiation. Now, gamma is actually part of the electromagnetic spectrum. Again, something that we will talk about further on in the physics topic. Now, electromagnetic radiation basically means that this is a wave. It has no charge, okay? It's got a high penetration, it's got a high energy, it travels at high speed, it travels over very large distances, but it is weakly ionizing. Okay, so it's not good at knocking electrons off lots of things. However, okay, when it does hit something, it will do a large amount of damage. Okay, and again, we'll get into that at a later date. The only way that you can stop gamma radiation is by thick sheets of lead or by a few meters of concrete. Okay, that's the only way that you can stop any absorption by gamma radiation. Okay, now finally today, we're just going to look at some of the quick uses of these. Again, we will go over these in more detail at a later time. But what you've got here is you've got the uses of alpha are in smoke detectors. Beta, it's thickness of sheets in industry. That will make more sense in a minute. And for gamma, it's usually medical. Okay, so chemotherapy, for tracers, and for sterilisation. Okay, now here's what I want you to do in addition to the work that I have set you on Google Classroom today. What I would like you to do is I want you to research the uses of alpha, beta and gamma radiation. I want you to tell me how it works and explain how it works for alpha in a smoke detector, beta in thickness of sheets in industry, and for gamma for chemo tracers and for sterilisation. If you can find any other uses as well, please feel free to pop those in. So this task is in addition to what I would like you to do with the worksheets that I have set you. Okay, so that is the isotopes and nuclear radiation. So next time we'll be getting into how radioactive isotopes decay and what happens when they do. But for today, this is all we're going to do. All right, so I hope that's clear for everybody, and stay safe and speak to you all soon. Bye.